Good morning, everyone. First of all, I would like to thank the organizers for giving me this great opportunity to present my results. Unfortunately, I cannot be with you in Bodrum. I got some little health issues very recently, so I could not make it to Turkey, even though I was really looking forward to joining you in person. Anyway, as I said, it's a great opportunity to present my recent work, and I hope we will still be able to interact, even though I will give you this talk online. Of course, if you want to discuss further these results, I'm happy to talk via Zoom afterwards or during the question session. So my name is Nicolas, and I work in Grenoble. By the way, do you see my pointer? Okay, yes, good. So today I will not discuss mountains or snow. I will speak about our recent observation of dual Shapirosteps in a Josephson junction array. So, but before we jump and dive into science, I would like to introduce the team. And more specifically, it's very important to acknowledge Samuel and Nicolo, who are respectively the PhD student and postdoc working on this project. They are really the main driving force, and I'm here to report their work. As I said, this is, of course, a bigger collaborative effort, and I would like to thank my colleague Olivier, Kater, Denis, and Wibke, who, again, provided a very important input and effort for this project. I also want to mention that Kater was with us in Grenoble for 6 months as a visiting professor. He is a professor at Washington University in St. Louis, Missouri. All right, so let me start with a short introduction. And the idea of this project is a bit broader than the dual of Shapirosteps, even though this is in itself a very interesting topic, of course. The idea is to somehow deal with the quantum metrology electrical triangle. And for those of you who are not familiar with this, let me give you a few hints. First, let's represent this kind of metrological challenge as a triangle. So the idea is to link 3 electrical units, namely volt, ampere, and hertz, via some quantum effect, or at least via some effects that are not depending on the size of the device, the way you perform the experiment. You really want to link these 3 units just by fundamental constants. And there exist already at the metrological level 2 legs that are covered. You probably know that voltage and current are linked via the quantum Hall effect, the quantum resistance. So I think now in the quantum Hall effect, integral quantum Hall effect, they are very nice plateaus, very flat. So you can really link voltage and current very accurately. Now, regarding the link between the frequency and the voltage, there is, of course, the AC Josephson effect and the famous Shapirosteps. So the idea is the following. You current bias a Josephson junction, and then you shine some microwave. So this is the IV curve, I mean the VI curve, I should say, without any microwave. And then whenever you add some microwave, you see some steps appearing. And what is remarkable is that these steps are quantized, and these voltage steps, they are exactly equal to an integer number times the flux quantum times the frequency. So as I said earlier, you see there is a direct link between frequency and voltage, and there is nothing but fundamental constant in between them. So this is also very nice. This works very robustly. Many metrological institutes around the world are using this effect. Now they are even making very long arrays of junctions to get even higher accuracy. I mean, that I could give a whole talk just about AC Josephson effect. However, this is not the topic of today. Today, I will show you how we could deal with the missing leg. So namely linking hertz or frequency and ampere or current. There have been many attempts in the past using single electron pumps in quantum dots, surface acoustic wave, or even superconducting electron pumps. Again, that could be a whole talk. There is a beautiful review if you are interested by Pecola and co-workers. So this is a very active topic, but so far this, let's say, technique, they were not based on a coherent quantum effect. So our idea is to find an alternative to these pumps, and this is what I will show you today. All right, so let me start with the AC Josephson effect and give you a cartoon of why do we observe these steps. So if you current bias a Josephson junction and look at its phase dynamics, it is very similar to what you would have in a washboard potential, in a tilted washboard potential, I would say. So if I represent the potential U of phi versus phi, and here I have the phase, like a particle that effectively represent the phase. You see that there is a tilt because of a current, but still the phase is localized in one well. And now if I somehow shake this well, because I'm adding some alternating current, you see that the effective particle might actually jump from one minimum to the other minimum. And now if you somehow compute what is the average current, what is the mean current, so you find that, right? Delta V is delta phi over delta T. So how many flux quanta are you passing per unit time? And of course, 1 over delta T is the frequency. So using this very simple, maybe too simplistic hand-waving argument, you can show that these steps, these voltage steps, they are proportional to phi naught times, I mean, the frequency. So now our ID, I mean, this is not our ID. I mean, as I will explain, this is a very old ID, but the catch here is to say, okay, we want to use duality between phase and charge. So phase of the Josephson junction and or charge across the capacitance of the junction. And then using this duality, we should be able to build a quantum coherent effect that is the dual of this Shapiro step. So if you want to link voltage, and frequency here, you want to be in this regime. You want a large EJ over EC ratio for your junction. EJ is Josephson energy, and EC is the charging energy of the junction. You want to be able to treat the phase as a localized variable. As I said, we can represent it in the potential. It's a very well localized wave packet. Then the washboard potential is a function of phi, the flux or the phase, and you are transporting fluxons, a quantum of flux, 1 by 1 or 2 by 2 or 3 by 3, and these are the famous Shapirosteps. Now, if you assume duality works, you want to be in the opposite regime for everything. So instead of having a large EG over EC ratio, you want it to be small. Instead of having a localized phase, you want to have a localized charge. And then your potential is not a function of the phase, but it's a function of the charge or the number of carriers. This is not called, I mean, this is another type of washboard potential that is usually called a Bloch band. And the cool thing is that now you would be transporting Cooper pairs and not fluxons. So this would be the dual of Shapirosteps. So as I said, this is not our idea by no means. It is definitely the work of Likarev and Zorin, something like 40 years ago. And so their bright idea suggested that it should be possible to engineer a Josephson system to really get the dual of the Shapiro step. So now let me walk you through this idea. So if you have a small EG over EC ratio, or EG on the order of EC, you can show that this Josephson Hamiltonian can be easily recast to Bloch band. So you're just saying, okay, I have a periodic potential, I'm applying Bloch theorem, so I should have periodic wave functions, and similarly to what you have in electron with a periodic potential in condensed matter, you will have also a quasi-momentum that we call the quasi-charge, and you have the effective potential that is, of course, periodic, and you have several bands, right? Now, if you really want to observe these steps, you need to restrict the dynamics of your effective charge particle to one band. Similarly, again, to what we've discussed regarding the AC Josephson effect. So you want your particle to live only on this band. So for this, you need to minimize charge fluctuations and make sure that whenever you have an effective charge particle, it stays here and doesn't go there. So this is actually very challenging experimentally, and I will explain you how to do this. Just for the sake of definition, what I will call EQ in the following is the width of the first Bloch band, and what I will call delta U is the separation between the first Bloch band and the second Bloch band. So basically, you want to avoid Landau-Zener tunneling. So this is the recipe of Likert and Zorin. This has inspired a huge amount of beautiful experimental and theoretical work, 40 years of work. So I could not cite them all, but again, this has been a very hot topic for many years, and many groups tried. So the challenge is, as I said, to localize charge, and I will explain you how to do that. But before going there, I want to repeat this tilted potential picture, but in this case, it's going to be U of Q and Q. So again, now you want a bias as well, your potential, but you don't current bias, your voltage bias, and you have this potential. Here, I'm also keeping the second band. And then similar to before, if you add an AC voltage, you might be able to transfer a charge per unit time. So if you follow exactly the same, I would say, reasoning, you can calculate the height of the current steps, and it's delta Q over delta T. So delta Q is 2e, or an integer number or times 2e, and delta T is 1 over the frequency. So you should have current steps, which are 2e times f. All right, so as I said, the devil is in the details, and more specifically, the devil is in the experimental details. Because in theory, as I said, you need Bloch band dynamics, so small EG over EC ratio. You need a localized charge wave function, and you want negligible thermal fluctuations, so your charge particle is very much localized. So on paper, it sounds easy. In reality, this is a bit of a challenge. So to get sure you have nice Bloch band dynamics or charging effect, you need a very small Josephson junction. In the literature, it is referred to as an ultra-small Josephson junction, so I will use this labeling in the following. The actual challenge is not to fabricate small Josephson junctions, because we have very nice nanofabrication tool nowadays. The challenge is to fulfill these two requirements at the same time, namely high environmental impedance and low temperature at the same time. So by impedance, I mean the impedance in parallel, or seen, if you want, by the small Josephson junction. If you have a low impedance, you will have the phase as a very well localized variable. If you have a high impedance, you will have the charge as a well localized variable. And it makes sense. I could give you a full derivation, but we can use a very simple hand-waving argument. If you put a very large resistance in series with your tunnel junction, it will be difficult for the charge to tunnel, so you have something like a Coulomb blockade, if you wish. Again, it's hand waving, but it's kind of Coulomb blockade. So you cannot tunnel, you can tunnel charges one by one only if you. So this is the hand waving argument why you need very high impedance. So we could think, okay, easy, then I can just put a very large resistance in series with my Josephson junction. And people try that, and there were some preliminary observations of this dual Shapirosteps. The problem is that you also want to circulate a current that is large enough so you can measure it. And then you're spoiled by Joule heating in your environment. So simply, if you put a very large resistance in series, you pass a current, R times I square becomes too large, you cannot cool down your resistance enough, so you are not anymore in the low temperature limit, so your charge fluctuates and you don't have this well localized charge state. So then we got inspired by these two theory proposals, and they explain very nicely that actually to provide a large impedance, you don't need a large resistance. You could do it with a very large inductance as well. So it's because the impedance of a transmission line is square root L divided by C. So if you make a very large inductance and you have a very small capacitance to ground, actually you can have a transmission line without any Joule heating because you only have a superconducting element, but still from the point of view of the small junction, it will be a large impedance. So this is what we implemented. So our device is made of a small Josephson junction, so a small EG over EC ratio. We used a squid geometry, so it's flux tunable. And then on the left and on the right, we used very long arrays of large Josephson junction, which can be seen as inductors and with capacitances to ground. So if you want, this is a non-heating transmission line on the right and similarly on the left. Usually in the literature, they are referred to as superinductances, so I will use this nickname in the following, but just view them as a non-dissipative high impedance. I mean, it is dissipative, but it doesn't heat up because of Joule heating transmission line. All right, so this is the device. I am an experimentalist. Maybe I should stop with theory now. And so we are fabricating what we nicknamed a block array because it's only made of Josephson junctions. So it's like a very long array of Josephson junctions. And so here you see the junctions in blue. And in the center, we interrupted this array by two here and there small Josephson junctions, and here you recognize a squid loop. So it's fabricated in one single lithographic step to make sure that the array is as even as possible. And also the little trick here is that we used a specific substrate. Instead of using the standard silicon substrate, we used a low epsilon fused silica wafer. I think we go from an epsilon of 12 to an epsilon of 4. So we are then reducing significantly the ground capacitance. So we are, if you want, boosting the impedance this way. If you want numbers, here they are. We have an impedance of something like 8 kilo ohms, and the width of the first Bloch band is 2.5 gigahertz, and the separation to the next Bloch band, to the next band, is 8 gigahertz. So that should be high enough, to prevent Landau-Zinner. And we have almost 2,000 junctions on the left and 2,000 junctions on the right. So another little novelty, but that was, I believe, key in this observation, is that we now are using a DC and microwave setup at the same time. So this is the block array. Here we have bias tube here and there. These are these blue things here and there. And so in the bottom, using the bottom arm, we can measure microwave properties. Using the top arm, we can measure DC properties. And again, at the same time, in the same fridge. And this is a close-up of the fridge. So now let's have a look at measurements. First thing we did was to measure an IV curve. Very simple measurements, I versus V. And what we observed are these nice peaks. These peaks can be understood relatively easily if you think about this array of Josephson junction from a somehow a BCS slash semiconducting picture. What I mean by this is that you just represent the junction as two BCS density of states facing each other. So what happens is that whenever you increase the voltage, one junction goes to the subgap state, so the current drops because it's a very high resistance, and then it remains low as long as the hole and electrons, they become aligned again, so you can flow a current, but then another junction will go to the subgap state, so the current drops again. And then you repeat this every time you reach an integer multiple of 2 delta. We are not the first to observe that. This was very nicely discussed in this paper from the group of David Haviland. Then we said, okay, do we understand this? So we somehow modified the theory or slightly adjusted the theory described in this paper. So what we did, the very simple, experimentalist level theory we did is this following. So we write just an equation of motion for this system. We have a voltage. We have, a very large inductance in series with 4 large Josephson junctions. Then we have a small junction that we model as a sign Q. So I told you about the cosine of the charge before, but since now we are dealing with the equation of motion, you need to derive the Hamiltonian ones, so you get a sign. And then we still have a little bit of damping in the system. This is 500 ohms, but this is enough cheap resistance, so it doesn't care if we don't care if it heats up or not. So if you take this
Nicolas,
system, you solve.
I'm sorry, I'm disturbing you, but you have 5 minutes left.
Okay, great. I will then speed up a little bit. And if you solve this equation of motion, you recover the peaks similarly to what I've shown you before. And now, using this model, what's cool is that we can also predict what should happen if we add an AC drive to the system. And what you see is that these peaks are still there. They are slightly lower, but importantly, before them, you see nice plateaus appearing. And these plateaus, they are at 2e times the frequency. So we were quite happy seeing this. So we said, okay, let's go to the measurement and try and observe these plateaus. So as I said, a key point for us was to observe the microwave response at the same time. So what we did was to measure the microwave transmission through the whole block array. So let's say that you input some microwave here and you measure what's going out there. What you observe are these double peaks. We described that in this paper already. So, but the idea is that, given the symmetry of the system, you have 2 types of microwave modes, the odd and the even modes. And if you follow this simple cartoon, you see that the odd mode, they will couple to the small Josephson junction because there is a phase bias across the small junction, while the even mode, they decouple from the Josephson junction because there is no phase bias across it. And then what we did was to add a pump, similarly to what you want to do for the observing dual Shapirosteps. And then, of course, you need to pump at the right frequency, the right power. The phase parameter is really huge. So this is why the microwave measurements are really useful for that. So here I am plotting a 2D graph where we have the pump power on the left and the spectroscopy frequency, the VNA frequency on the right. And what you see is that if you are at the right power and at the right frequency, you see some kind of mode that is now synchronized with the pump frequency. So the pump frequency is this faint line here, and this is the block array response. And you see that right here at this power around -5 dBm, something happens. And if you now measure the IV curve without touching anything, this is what you observe. So you still have the peaks, as I told you, but now before the peaks, you have nice plateaus, which are quantized, and they are quantized as 2e times the frequency. Of course, now you might wonder, okay, are these really dual Shapirosteps? Is it really flat? So of course, we are very concerned about that. So what we did was to sit at a given voltage. So you say, okay, for example, I choose this voltage, then I ramp up the pump power, keeping the voltage constant, and I measure the current. So what you see is that the current increases, and then it plateaus, again, around -5 dBm, and then, of course, it might eventually increase further if you keep increasing the power. We pushed this analysis one step further. Instead of just measuring the current versus power, we used the lock-in amplifier to measure di over dp, and you see that this goes down 0. The derivative, if you want, is 0 at -5 dBm. So this gave us a strong confidence that what we are observing are probably dual Shapirosteps. Now, of course, the next thing you want to check is the frequency dependent, because I promised you that this current should be 2e times f. Of course, then what you want to do is to vary the frequency. So this is what we did. Here I am plotting current versus pump frequency, and you see that we observe nicely aligned dots. But for this point, around 5.5 gigahertz, we observed steps, but they were not stable, they were jumping, so we don't know what happened, but anyway, this is what we observed. For the sake of clarity, on this large graph, I am plotting the current versus the voltage for these three different pump frequencies. So of course, code color is the same. Dark blue, light blue, and medium blue, they are for these three different guys. And you see that every time you see one plateau, and one plateau. Now, if you are interested in the somehow metrological performance of the device, we are very far from any metrological accuracy. Let me be very clear. Of course, this is a fair experiment, so this is somehow expected, but still it's promising, because if you plot the relatives, you see that we have well below 1% precision and accuracy for this first measurement, maybe something like a couple 10 to the -3 precision and accuracy. But again, this was not the topic, the main goal of this first study. I guess it's time to conclude. I see it's 11 on my clock. So as a conclusion, we've implemented the proposal of Likaref and Zorin. We could finally observe dual Shapirosteps, because we implemented the high impedance environment using superinductances, and also because I believe we use the DC and microwave setup. Of course, it opens many new opportunities. Obviously, we don't understand all the details, so there are a lot of physical questions. Then, from an engineering point of view, we can probably improve the array a lot, increase the current, make flatter plateaus, and of course, maybe one day we can close this electrical quantum metrological triangle. So our work is now available on the archive, and I hope you went and see Oleg's talk yesterday. There is a very beautiful work from Oleg Astafyev and Yevgeny that was published on a similar topic very recently. They are not using Josephson junctions, they are using nanowires, but I believe that their work is kind of similar to what we are showing. With this, I stop, and I thank you very much for your attention. Hello? Anybody here? Maybe, can you hear me? Okay.
Okay.
Hello?
Yeah.
Can you hear me?
Okay. So it's probably something is going on there. So
Can you hear me?
Yes, we hear you.
we hear you. The question is whether you hear me.
Yeah, no, I hear you perfectly. There was maybe 30 seconds where there was no sound, but now I fully hear you.
Okay, so shall I continue? Or?
With pleasure.
Yeah, okay. So in order to keep your system in the lowest band, it's not sufficient to control a J over a C ratio, but you have to have some portion of dissipation. Otherwise, sooner or later, your system will go to higher bands due to Zener tunneling, okay?
Absolutely.
Yeah, so the question is, what is the mechanism, the dominating mechanism of dissipation in your experiments? Is it due to plasmons in these transmission lines which you have on both sides of your junctions? I mean, these transmission lines formed by a series of junctions and, yeah.
Yes, absolutely. Yeah, so indeed, these are transmission lines, so you have plasma modes, and then eventually they are connected to the outside world. So yeah, this is we believe the main dissipation channel. Yeah, absolutely.
Okay, and also this dissipation should lead to some broadening of these block steps. I mean, you use this dual Shapirosteps, but originally Licharev uses block steps. But anyway.
Sorry. I mean, the terminology is a bit wide. Yes.
This is not the point. The point is that if you have dissipation, you have broadening of your steps. So
yes.
you're basically saying that your dissipation is large enough to keep the system in the lowest band, but small enough not to have large broadening.
Yes.
Yeah. So this is possible. Yeah. To choose the parameters like this.
Yeah, so these are the two parameters, width of the block band and separation. So you see there is a factor 3 in between them. And when you put numbers, if you calculate Landau-Zener, it's very, very, very small.
Yeah, okay. Thank you.
And now regarding maybe your question about the link between the width of the step and the dissipation, this is something we don't understand for now. That we don't know. This is an open theory question, I think. Can we link?
I mean, I can comment that we have a paper with Dima Golubev many years ago, which was basically in the times of Kuzmin and Haviland experiments.
Yes,
on this
yes.
one. And so
I know there are many papers we tried and compare to our experiment. It doesn't completely fit. I'm not sure that in these papers the plasmons are taken into account properly. I mean, back in the days, this is what people were doing. So
in that case, it was ohmic dissipation, but it doesn't really matter. I would say it doesn't matter much. But we can talk later, perhaps.
With pleasure.
This is an important issue. I mean, the width of the steps.
Oh yeah, this is the next thing we want to understand, and so currently we don't. Yeah, I fully agree.
Yeah, thank you.
My pleasure.
Okay, thank you. Next one, please.
I would like some comments related with dynamical equation for quasi-charge. Yes,
one?
this one. Here, actually, last term in left side is not sinusoidal, but this one is periodical function. But you put in similar to Josephson case, to phase case, sinus pi over A and Q. But really it's different. But maybe for your purpose, this one is enough. But sometimes it seems dangerous. And the first term also, inductance is Q-dependent because of there are calculations of Alexander Zorin related this moment because of block inductance, so also a periodical function of quasi-charge.
Yes. So what is the? Should I comment, or do you have a more?
This one comment, general comments.
Yeah, no. Okay, it's a comment. No, I agree. So you're right. This sign of Q is absolutely an approximation. we did that because we don't know how to do the full calculation of what you're suggesting is that this is a first Bloch-band approximation, and of course we should also take into account the other higher Bloch-band. I fully agree. Here, if I understood correctly, you're saying that, okay, describing this block array as a simple inductance is also probably too simplistic. And I also fully agree. Currently, we are now trying to work out a theory to really, instead of having a large inductance, really keep the dynamics of all the junctions. But since there are 4,000 of them, it's a bit of a challenge theoretically. But yeah, I fully agree. Sign Q and treating the array as an inductor is definitely too simplistic. Did I get your comment correctly?
Yes. Yes, thank
Okay.
you.